Experimental hardware and instrumentation, accelerating the pace of engineering education. That's the topic for the next approximately 90 minutes, maybe a little bit less. And let's just imagine what you could do if you would have a device running on a line like this, and we will see that later how it can work. What could you teach with such a device besides just control design, besides just embedded systems design? And we will give a look to such applications later in this presentation. But the main thing I wanted to show you first is a demonstration that involves multiple different disciplines. And I will do so using a Raspberry Pi to which a webcam is attached. That webcam sits on top of a small electric motor. And that electric motor is hooked up with the Raspberry Pi using an Ethernet connection. And what you can see here, let me give you a better impression of what is happening here by showing you the actual output of that very camera. So this is what the camera sees, and this is what the appropriate state chart to the system looks like. And what else do we have? We have also a chart showing us the position. Here we go. The position of the ball on the image. And so if I now put the green ball in here, you can actually follow the ball. You see, if I just move it vertically, you see the yellow line changes. If I move it from right to left, the magenta line changes. And if I move it out of the frame, you see instantly the blue colored rectangle changes its position because the system goes into a state where it says, I can't find any green ball anymore, so let's do something different. Then once again it catches in and it follows the ball. Just imagine what you want to teach your students using such devices. Starting with image processing, going to communications modeling, system communication, over to control systems. And just imagine what you could do when your students do real stuff. Let's dive in to the presentation first. So the main purpose of this talk is to encourage you to use existing tools in and on MATLAB with hardware instead of reinventing the wheel. So that's really the purpose of this presentation. Now, why am I telling you this? Well, I have a little bit of background in automotive. Then, in parallel, doing my PhD at Technical University Munich, doing some more automotive, and then going to MathWorks, the makers of MATLAB and Simulink, and now engaging with academia in helping teachers, professors to adopt model-based design, MATLAB and Simulink for your education. The remaining talk is structured as follows. We will have a look at the various challenges for teachers, for industry, and also that students see in the current way engineering studies are conducted often. To then go over to a section about engagement, how to drive student engagement, and then also reusing, integrating, and sharing, and end with creating things. Now let's have first a look at the teachers. So what do teachers see as struggles in university education currently? Well, in a recently conducted STEM, which stands for Science, Technology, and Mathematics, in the UK, we asked, are there enough skilled candidates from universities to meet STEM employer requirements? And we asked both industry leaders, but also academics. And you can see the no replies of the academics in the yellow bar. 79% of academics said, well, actually we don't feel we're already there and providing enough skilled candidates. So short answer, no. You can find more about that at mathworks.com/STEM skills. And no need to write it down. As far as I'm concerned, this presentation is available to all of you afterwards. And going more into detail, it's 61% of business leaders and even more of academics actually believe it will take more than 10 years to close this gap between skills required and skills provided by universities. I was staggered by these humongous numbers, but even more staggered that also the collaboration between universities and industry is not really rated on a level where it could be, neither by employers nor by academics. The good side of that is that both of them are relatively self-critiquing, so which means they're aware of these problems. And coming also with that is that a large portion of industry think they really should have a greater say in curriculum. And also that's greatly welcomed by universities. So absolutely, the companies should engage with universities. Yes. And when they do, good things can happen. So let me show you an example from the university where I did my undergrad studies with, the Applied Science School in Augsburg. So Professor Stark from the computer sciences, he's using high-level language like MATLAB for actually programming a robot. And why is he doing that? Because he says, I want to get to results faster than in programming. Trajectory planning is one side, but trajectory programming is a different side. And so he's saying, well, I want my students to have the skill of planning and programming trajectories, but I don't want to send them to program several pages of C code to reach something that they could achieve with much less MATLAB code. Now, moving over from the academics view to the industry view. So the same study conducted in the UK about the STEM skills gap also brought some quotes which I want to show to you, where one senior manager in industry said, well, it's really particularly hard to recruit graduates with the key skills required to make an impact. That's always the point, to make an impact, impactful. That's what they want. Another quote that I want to show to you is, well, he complains about the silo thinking still predominant in some parts. And the question is, how can we overcome this? And referring back to the topic of this talk, how can we overcome this silo thinking also with hardware experiments? So, summarizing those two parts is, what they want is, employers want abstraction and big picture thinking, but really solving real world problems in multidisciplinary teams. And if you just think about the teams that you personally are working in, then most likely you will be working not just with the same breed of engineering that you graduated with, but with very different kinds and kinds of people. Computer scientists, mathematicians, electrical engineers, mechanical engineers, bioengineers, whatsoever. It's a highly collaborative environment in pretty much all industry outside, and increasingly, and I'm very happy about that, also in universities. Now, if we look to the triangle, industry, education, and also research, of course, we can say that, well, on the lower half of this chart, you see there's the university world with research and education. And then in the upper part, you have the development channels in industry. But all of those do this conceive, design, implement. Here it says produce, but we could also say operate, and then have the CDIO methodology. So it's starting. And providing the skills really is important also for recruiting. And recruiting both in terms of going from education to research, but then also going from education, of course, into industry. And as one example where this collaboration between industry and university is already working, I want to highlight another example from my direct environment, and you will quickly recognize that I love sticking with those that I personally also know. With an example from the Technical University of Munich. Florian Holzapfel chairs the Institute for Flight System Dynamics, and he really says this collaboration with industry is important, and therefore for him it's also important to use the very tools that are being used in industry, because he can provide skills using the tools. So it's not about tool skills, but it's about skills that need the tools somehow to actually be able to have an impact then in the industry, to be able to really develop solutions for real aircrafts and partially even real time in class. That's what he does. If you want to know more about Florian Holzapfel and what he's doing, just search for his name, Florian Holzapfel, MathWorks, and you will find also a video on that, where he explains all that. Now, going over to, or staying with the industry part a little bit. If you think back 25, 30 years, what did happen then? Before that, there was still a lot of hand drawing in construction going on. Some of you may still remember that time when there was a lot of hand drawing in construction, and especially mechanical engineering. And then, what did happen? Yeah, slowly the CAD programs kicked in. More and more CAD computers were being used to actually draw the designs that we're sitting in today, flying in today, driving in today. And today, rarely anybody is really doing hand drawing for industrial design. So what happens now, model-based design disrupts engineering together with simulation. This is what's happening now, that more and more people in industry and more companies, they don't do handwriting their algorithms anymore. They're using models and simulation to figure out what they are doing. And as an excerpt, let me give you the 4 practices of early verification. What does industry really do and why are they doing it? So, starting with practice number 1, create and simulate a high-level system model during specification stage. Why and what does that mean, and why creating a model when I also could try to create it in real life and with prototypes, like we did it for a long time now? Well, actually, if you simulate the behavior of a high-level system model, what do you gain? You gain system insight. You gain system insight beyond the level what you usually could do even with real testing, because you can instrument the model in a way that may be too expensive or even impossible to instrument the real system. You can look what's happening really inside, where you don't have any sensors to put in the real system. And so you even better understand the system that you're trying to create, and thus also understand the dynamic behavior of that system, which can not only have an impact on the algorithms of your system, but even on the system architecture. Leading to the practice number 2, which is please test from day 1 with multi-domain simulation. Still, we see a lot of people waiting with testing and creating a lot of artifacts and then putting it all together and then realizing, oh, it doesn't really behave like it should. And maybe the error or the mistake was made much earlier, when they thought about the system, when they first created the system in their minds. And And to overcome that, use multi-domain simulation. Why that? Because it's much easier to change models versus changing wires in your setup versus working with steel and asking your prototyping folks downstairs, well, could you provide me with another chassis that looks more like this and not like that? It becomes very expensive, and also it's easier to change models than actually recoding all the time when you maybe change even the hardware platform because the one that you thought first does no longer suffice your needs. The third best practice is create a virtual test suite that stresses the system. Once you have the model and you're improving the model and increasing model fidelity, what should you do? Well, really stress the system out. And why should you be doing that? Because, well, simulations, dear folks, scale better than real hardware. If you're testing on the real device, let's imagine a car manufacturer, you can only produce so many prototype cars, and it's a very expensive process. And you can only drive so many real kilometers with those cars. But if you have simulations of the relevant parts of the system, you can scale it up anywhere you like, because computing power, with all the cloud computing that's available now, is virtually limitless. And so you can even drive maneuvers in complexity and also combinations that wouldn't be possible otherwise. Leading to practice number 4, then please use model and test suites as a reference design. Use them throughout your design and reuse them. Which means if you had created the model, designed your thing, then go to the implementation using automatic code generation and into integration. You can really reuse the same test scenarios that you already had in simulation and reuse them in the implementation phase. Regardless of what your design contains, whether it's just limited amounts of controller and plant models, maybe there's more algorithms involved, maybe you even have temporal logic, you have mechanical parts, whatsoever. And then really checking that against the specification, against the requirements. And then also checking that again with the implementation, regardless of whether you generated C, C++ out of the models, or VHDL, or Verilog, or structural text used in PLCs. Doesn't matter. And then also, in the integration phase, again, you use the very same test scenarios. Now let's come to the third challenged group, which is the students. Each year, there's a study going on in Germany measuring the quality by asking students, what do you feel about the classes? And in the study Quality Monitor Germany 2030, two things stick with me. First was that in more than half of the cases, teachers present the subject matter as interesting and appealing. Only 40% agreed, which means the other 60% most likely didn't agree. And also only 30% of the students agreed to the sentence, the teacher is able to motivate students for subject matter in more than half of the classes. Those numbers are really a wake-up call. And the question is, how can we all work on improving that quality? How can we all work in making the classes that the students see more engaging, more motivating, giving them more context and more meaning? Well, now why is this guy from MathWorks standing up here and talking about student motivation? Well, in the same way that you create spaces, that you create buildings for your students, that you use electricity to light the buildings, well, in the same way, MATLAB is part of the scientific infrastructure of academic and research organizations. And take just the picture of a concert hall. Like a concert hall for orchestras, really, MATLAB is part of that. So, what part of that is it exactly? Well, I'd say MATLAB is neither the music, nor the instrument, nor the musician, nor anything. It's the space where the musicians play together with other musicians, and finally they enjoy music. This is what MATLAB wants to be. And this is also why we're having this session. So, what do you need for a musician? Well, obviously, thinking about a musician, what do they need? They need enough seats, right instruments, and a couple of other things, allowing them to communicate better with each other, to communicate also with the conductor, and to produce really stunning results that we then enjoy to listen to in the concert hall that we just saw. Now, moving over to the analogy, what is MATLAB then for the educators and for researchers? Well, sure, you need enough MATLAB with the right set of tools. And as before, the standard notation here, the standard language, an operating system. You still need all that means of communication. And of course, you also need education and training. Which does not mean that the training on the tool has to happen in class necessarily, or happen at university. Just in the same way that usually in an orchestra you don't get piano lessons. You're expected to come with a very good skills in piano playing already. And so the same applies here as well, but then using those skills and relying on those skills. And for example, the Politecnico di Torino, Massimo Violante really says what he's doing with MATLAB and Simulink and also Stateflow and the code generation. And why is he doing that? And I'll give you just a couple of seconds to also read what Massimo Violante is saying. And if you have the chance to meet Massimo Violante, he's a wild traveler to all sorts of conferences and events, so the likelihood of you running into him is given. So be sure to ask him, and you will be able to witness, especially about the rigorously validating, testing, and debugging it. He's very serious about that part. He pushes his students through the part of really validating what they created. Not leaving them off the hook and saying, yeah, it looks good and theoretically it should work. No, he actually makes them creating the system and running the system. He's one of the big heads and big proponents of Freescale Cup, where students produce algorithms for small cars like an A4 paper, running through a track where they have to use a line camera recognizing the track. And then, well, what do students say? I would have preferred to show it to you with a live demo, but unfortunately I don't have internet access on this machine. So let's just watch a short video that my colleague Gareth here created. Well, if you go to LinkedIn and you go to the alumni section, you can search for a specific university and then search, if you scroll to the right a little bit, search for the skills that students specify in their profiles. And in many cases, you will find students giving MATLAB on their profiles as a very, very interesting skill. And just the amount of students that specify MATLAB as a skill means something to me, because that means they're seeing that as an important skill for getting employed. Try it out for your own university, try it out for neighboring universities, and see how are we doing compared to places like MIT, compared to places like Polytechnic di Torino, to places like KTH in Stockholm. Just compare yourself to the places and look it up. Coming to what can we do about it? How do we really drive this engagement? And again, I would like to show you now the demonstration that involves this Sumo bot here. So in order to do that, let me first unplug this device here. Take it off. And show you my screen, which also means we can stop the model that we previously used. Stop that, close it, close also this, and also close the Simulink project that we just had. And go to the Sumo. So let me show you in model here, verifying that Okay, what effectively we want to do is we want a robot to follow a line using only some light sensors. And what you see here with a fairly simple PID controller, of course the robot will somehow oscillate over the system, over the given track, but finally find its way if using only 2 sensors. You of course could make it more precise by using more sensors. So this Sumo bot, which a company called Pololu produces, it has a number of light sensors on its lower end, but we're, for the time being, and for simplicity's sake, are just using the 2 outer ones. So now that we've seen a simulation of this, we want to deploy this to the real system. But first of all, let me show you how you would usually start with such a system. So let's just start with a blank slate, and let's just take a sine wave with an amplitude of, I don't know, 255 maybe, and using frequency of 2 pi. So then we would need the library that one of my colleagues created for this Sumo bot, which allows us Sumo motors. And as you can see, the Sumo motors block has, by the way, whom of you has seen Simulink before? Just show hands. Some who has not seen Simulink before? Some who has seen MATLAB or used MATLAB before? Not? Okay, good. So, but you quickly will get how it's working, because what we now do is, we connect the sine wave with the left speed, and we also connect it with the right speed, because we have a left motor and a right motor. So now we have to tell this newly created model to actually run on a target system. And in order to program that target system, I will need to plug that in. So let me just pull out the cable here. And the system, of course, is based on an Arduino Uno. So I just select Arduino Uno. And let me just plug that in. So it's now connected to the computer and can run on that. So of course, when I want to generate a sine wave on it, I have to specify also what sample time I want to use. Because the normal sine wave, created to be as precise as possible, we don't need that. For us, it's totally sufficient to have a sample time of 0.1 seconds. And then once we have done that, we can deploy this to the hardware. So what it now does in the background, it generates code out of this system, transparent to the user. It then downloads the software onto the Arduino platform using the USB cable, and we're done. This will take a couple of seconds because between code generation and deploying, of course, lies compilation. So all of that is done by the normal compilers that are suited for the Arduino board, which you can get as a target support package directly from Simulink. And I will show you how to get that. Just a couple of seconds to finally do that. Once it has finished with compilation, it's downloading, and then it says model successfully deployed to Arduino Uno. You can see that. Oh, it's ripped off here. Model successfully deployed to Arduino Uno. So now I can unplug the USB cable. And what should happen now if I switch it on? It oscillates. It's a sine wave. Now, how many engineering professors do we have in this room? Some? Good. So let's try out something. Let's try out something. I have a task for you. So let's drop an additional block in here. And let me drop in a, what do we take to make the system more interesting? Let me put in a delay block. Delay length 0.1. Sorry. Of course I have to. Yeah, so that's fine. So let us put this block in here. Just rewire. And rewire here. So, question for you: how will the system behave deploying that? What trajectory will this device follow? Pardon me?
You'll go in a circle.
In a circle, you think? Other opinions? Any other opinions? Do you all think a circle, or would it be something different?
Well, this is speaking something different.
Yeah? Okay, so kind of a zigzag, a jigsaw. Okay? Let's try it out. Let's try it out. Maybe I should do this on the floor. So you were right. Great, thank you. And of course, if we had more time now, we would have built a simulation before, in the same way that we had done this with the other system before. Because the real catch is now, don't need to save this, the real catch is now, you saw the simulation of this model. And now, if I just type sim equals 0, the behavior of that model will change. Because while I formerly have used a variant subsystem configured to build the simulation model, it's now actually using the I/O blocks in the Sumo bot. And if you have never used variant subsystems before, you may give it a try. Let me quickly show you the block parameters. You see, this is a variant subsystem where you can supply multiple different ways that a subsystem could behave. You configure that using, for example, simple workspace variables, but you can also construct more complex things. And looking in here, you see there's two different variants for this subsystem. The one is grayed out, the simulation part, and now the target part is live. And if we deploy that model in the way we configured it to the Arduino, again, first it has to build, which means generate code out of the model, then preparing the model, which means compiling, linking it, linking the code, downloading it to the Arduino, and then it's done. Unplug the USB, and let it run in circles here. Oops. That's live. So with a fairly simple device.
Sorry, what's on the table? What's on the table?
Pardon me?
What's on the table?
On the table? Oh, sorry. On the table, we have just some tape on the tablecloth. Just some black tape. So it recognizes the difference between light and dark, and then tries to follow it until it starts to rip off the tape from the tablecloth. Good. Are we good so far? Got the idea? Okay. Then let's move on. So about engagement, we're engineers, so let's engineer our way out of this dilemma. And this is exactly what, for example, the guys at the university, the RWTH Aachen, have done. So what they have created is a class for project-based and problem-based learning in the electrical engineering realm. They're using this Lego Mindstorms devices. They're still using Lego Mindstorms NXT because that was the current version when they started this class a couple of years ago. And the lecture is designed in a way that they do cover signal processing basics, mathematical models, and also an introduction to MATLAB. Doing that by really having some lecture each week and also some tutorials and then also small group exercises. And this happens in the very first semester, first year. So not something first do a lot of theory and then we'll let you create the real deal. No, they do this in the very first semester. And why are they doing this? Well, or when are they doing this first? Part of that class is a workshop called MATLAB Meets Mindstorms. And this happens in December, so just 2 months into the first semester. Think about your own classes. How much can students do after just 2 months into their studies at all? So this is an 8 days course program. The whole department of electrical engineering is there. So all the different institutes have to assign faculty to this from different backgrounds, different flavors of electrical engineering. On the right lower corner, you see the number of students undergoing this program. So kicking to 500 students in the last year. So really massive numbers. So this is not a small scale class, it's really a large scale class. Every electrical engineer starting at RWTH Aachen will go through that class. And it receives great student feedback. It's in fact the highest rated class on the whole university. And how do they do this? Well, in the end, in fact, they're creating a laboratory where they're playing or experimenting with mathematical models, practical engineering, and then of course using some language, MATLAB in this case, for actually creating things. Showing you the schedule, how this 8-day workshop after 2 months looks. First, they accommodate themselves and get introduced to the various sensors, the brick, the sensors, and then the last 3 days, you see the creative tasks up here. Then a final presentation. And some impressions of that class you can find here. So they're creating devices like Morse code readers and writers. So reading and first writing Morse code on long sheets of papers. Or even creating a 3D object scanner, all with Lego Mindstorms, and programming that in MATLAB. And then they have to present this to a larger group and show what they have done and how they did it. And the reason the Aachen University is doing that, they say, okay, after 2 months, they have some basics in mathematics already. They have a rough understanding of what engineering could be, but what they really need is some context setting. They need a context on why in the next couple of years they have to go through things like control theory, adaptive controllers, PID controllers, all that stuff, signal processing, why they have to learn all the theory. Because in that class, they quickly realized what they already know, but also the vast amount of information and knowledge that they do not yet possess. And so they can see what can be done with engineering, but needs a very, very more sophisticated level of engineering. And so they are much more appreciating the theory-heavy classes later, because they know, I knew I would have needed something more advanced to actually make my project even better, but I didn't know it back then. So I need the theory to be able to create such things. And this motivation they're using throughout their studies. But also for the educators, there's some big benefits in it. Looking to the CDIO syllabus, which we have seen yesterday in one of the other sessions. So what do students praise? They really praise that it's a collaborative learning environment. They create these things in small teams, 2 to 3 people. They create something together. They see a success if their robot does something meaningful. Small devices like a machine that throws paper balls into a bin, things like that. Getting motivation from it and really having a positive experience early on in their studies, which keeps them going. But also, this enhances faculty teaching skills, because it really involves all departments, all institutes of that department. And they use that for dissemination of teaching knowledge and methods by really other teachers relying on the fundamentals taught, which means the disciplinary knowledge, MATLAB know-how, but also teamwork skills. But also the student teaching assistants are required to participate in a class to advance their personal teaching skills. So it's not just that robotics or the MATLAB meets Mindstorms class, there's also an infrastructure created around that. Because remember, it's around 500 students going through that class, so you really need massive amount of tutors and teaching assistants helping out the students to achieve successes. And when you then have highly motivated students which really get the grasp of engineering, then they can also go on to projects that even more motivate them. And maybe they become participant in a student competition like Formula Student. Who knows Formula Student or has heard of Formula Student? No? So let me show you a video of what Formula Student, especially Formula Student Germany is, and what it means to students. So I highly encourage you to check out Formula Student. There may be a Formula Student event near or in your country as well. There are different events. And we happen to specifically support Formula Student Germany, Formula Student UK, Formula Student Japan, Formula Student North America in Michigan, and also the Formula Student China. Check it out. And if those competitions involve really teams from all over the world. So from the Student Germany, we have people from India, from Egypt, of course from the European countries, some from the US that you saw in the video. So people from all over the place coming to Germany for this competition, which is not just a race, it's really a design competition, as Tim Haneke explained. Check it out. So coming to the next part. So now that we have engaged students who really kick ass in doing what they should be doing in their studies and doing even more, how do we reuse what we have done there? How do we reuse concepts? And that's actually the next part. Because, well, when you think about experimenting, there's also some research on that and saying there is no correlation between experimenting and learning outcome in general. Let that sink in. So just because you do some experimenting, that doesn't guarantee you any learning outcome. It has to be done in a correct and right way. Because it then also says, the study, experimenting does improve the learning outcome if supported by a didactic framework, of course. So going through the 5 steps that an experiment usually involves: prep work, pre-experiment, experiment, post-experiment, and evaluation. You see, the pre-experiment is really very, very important. The post-experiment is immensely important because that's when the things that the students saw and went through can really sink in. But funny enough, most effort so far is spent on the experiment, which is typically overemphasized. And let me show you some ways how to make things easier and how to use tools to make things easier. Because that's one of the parts where MATLAB and Simulink can help, really in part 1, 3, and 5. That also tells you what requires you as humans is pre-experiment and post-experiments. That's where you as a human are required. In everything else, tools can help. As a simple example, very, very simple example, let's use an RLC system, so a resistor and a very simple oscillating device. I'm sure pretty much everybody of you, especially from electrical engineering, should have a grasp of that. If you're from mechanical engineering, you will quickly notice that the very same system is possible with a spring damper. It's the same system, same mathematics behind. And we will see in the next couple of minutes how you actually can use tools to really move from one representation to the other. Move from a symbolic analysis of that system to a numeric analysis of that system, and then also a graphical and system model. Now, the solution landscape, how does it look like? We will first go through a little bit of symbolic math using the MATLAB part, then creating a numeric solution out of it, and then using also the symbolic solution and create a Simulink block out of that, and then also a physical modeling representation out of the very same equations that we define. And let me show that to you. So first of all, about the problem. If you use Kirchhoff's laws for the RLC series circuit, well, since you're academics, you should be aware of those equations. Not that difficult, and actually, if you use a spring damper system and Newton's laws, you quickly realize, well, the equations look the same, just the alphabet is a different one. But it's really the same math behind. So whatever you're from or your students from doesn't really matter for the math that lies behind. Now, when we solve this with pen and paper, and I absolutely encourage you to teach that to your students first, they have to go through that process of really hand calculating and solving such systems by hand to later be able to appreciate the use of tools. They can create step response, frequency response for that system, and with that Bode plots on the right, then get a better insight to the system, and of course acquire the skills how to get there. But once they have learned this, maybe then it's time to use some tools actually to move forward. And let me show to you how that could look in reality.